So we have so far discussed the two sections, the two parts of moving charges. Now we are moving to the third part of this physics lecture series. Tangent galvanometer. This is a device used to measure current. Its principle is B is equal to BH into tan theta. BH into tan theta. Let us consider a magnetic compass. You've got the needle indicating north and south, and it is subjected to the magnetic deflection, that is deflection due to the magnetic field. So this deflection is influenced by two important magnetic field. One is the magnetic field B due to the current in the coil, So this is the perpendicular coil and this is the magnetic compass. You can see the pointer here and you have got the magnetic needle. So B is the magnetic field due to the current in the coil. We have already seen what will happen when we keep any point at the at the center of the circular coil. Okay, so B is the magnetic field due to the current in the coil. So this is the coil. It may have n number of coils. So we have so far seen a coil, a circular loop. Now we have 200 coil, 300 coil, 500 coil, 800 coil, like that. So you have n number of turns of coil. Do you understand? Right. Now B is equal to magnetic field due to the current in the coil. BH is equal to the horizontal component of Earth's magnetic induction. It is the horizontal, that is the influence of the magnetic field of Earth. So the horizontal component of Earth's magnetic induction is indicated by BH, right? The magnetic field is suspended at a point where there are two cross fields at right angle to each other. So it is because of this it will come to rest in the direction of the resultant of the magnetic field. So this is the tangent law. So it means tangent law, that is a tangent, the tan of deflection of angle, that is a tan theta, is the ratio between B and BH. So the tangent law, simply it can be mathematically represented as B is equal to BH tan theta. That's all. So it means the magnetic field due to the current passing through the circular coil, that we already know, B is equal to mu 0 Ni divided by 2A, right? Where K is the reduction factor. So in this case, K is equal to reduction factor. We can put the reduction factor of the tangent galvanometer, that is given as I is equal to K tan theta. So now we can equate these two equations. Let me consider this is equation number 1, this is equation number 2. On both sides LHS are equal, so RHS should be equal. Therefore, mu 0 Ni divided by 2A is equal to BH tan theta, because equation 1 and 2 have LHS equal. Then from this we can measure the current, that is I. So you can bring everything to that side. So 2A BH divided by mu naught N tan theta. So this I is given as K tan theta and K is substituted here as a constant. That is, that constant is nothing but 2A BH. For simplicity we have introduced this because all are constant. For instance, A is constant, is it not? And BH, that is also constant. Mu naught is constant. Number of turns, after all, we are fixing arbitrarily as a constant. So all put together, that can be called a constant, and that is why it is reduced. All these constants are reduced in a tangent galvanometer. So it is called a reduction factor of the tangent galvanometer. So K. So that's what we are given here. Do you understand? So we can replace this big ratios of constant as small k, I mean capital K with a simple single letter. So I is equal to K into tan theta, right? Then Ampere's circuital law. So integral over the cycle B, that is the magnetic field, dot dl, the differential element, the small length element of the conductor, is given by mu naught I naught. It means the line integral over the cycle, that is we have to take the entire length of the conductor, even though it is a circular loop. So B dl for a closed curve, is equal to mu 0 times of what? The current, net current, okay, through the area bounded by the curve. That is known as Ampere Circuital Law. Circuital and circuit means closed. And then magnetic induction due to the infinitely long straight current carrying conductor. This we already know. So B is equal to mu 0 I divided by 2 pi A. And here B of 2 pi A, we can multiply this, that is equal to mu naught I. So you can equate this. Therefore, we know that is when I say this is the circular coil, is it not? This is the radius of the coil A. So in that case, 2 pi r is the circumference of the coil, is it not? So that is the perimeter of the coil. That can be taken as 2 pi A, that is L. So we can simply put L also instead of 2 pi A. So you can put BL. So you can make use of this equation also. So BL is equal to mu naught I naught. Then in a more generalized way, Ampere's circuital law can be easily written as integral over the cycle what is B? Magnetic field vector dot the length vector of the current carrying conductor is equal to mu 0 I 0. Then we'll move to solenoid. Solenoid, it consists of long wire wound in the form of helix, where neighboring turns are closely spaced. They are very closely spaced. So this is a coil, n number of turns are evenly, that is wound up like this. Okay, so that is known as solenoid. Now each turn is regarded as a circular loop, is it not? This is circle 1, circular 2, circular loop 3, etc. So in turn, we already know when a current goes in this way, there is are you able to see the planar magnetic field? Okay, so here it is in the anti-clockwise direction. So this is clockwise, this is anti-clockwise. It goes inside, it comes outside. So coming out from the plane of the paper. So in that case, it creates a circular loop where it is when these circular loops are kept adjacent, aligned adjacently, what happens? It makes another horizontal circular loop like this. Are you able to see this? And similarly this. Okay, then what about this? Here it acts something like a bar magnet almost. Okay, so the magnetic field will be, we already know they never intersect each other, so they go just like that. So you can see a lot of parallel lines here. So each turn is regarded as a circular loop, as I already told you. Then, and what about this wire? When you may have a doubt when these wires are when these wires are kept wound so closely each other, then there is a short circuit. There is a chance of developing short circuit, is it not? How to avoid that? Best thing is it is insulated. It's called the insulated varnish. Okay, so with a coating of insulated varnish, we can avoid the contact by the wires when they are kept very closely wound up each other. So that is called the enameling. That is a special kind of varnish that is having insulating property. So they are wound so that the turns are insulated from each other, right? Then right hand palm rule. Right hand palm rule means when a coil is held in the right hand, assuming that we are holding the coil with the right hand like this. Okay, are you able to see the thumb? So the thumb indicates, extended thumb points the direction of the magnetic field. Do you understand? The extension of the magnetic field. This indicates the magnetic field. This is the extension. This is the magnetic field. It indicates the extension of the magnetic field. So the so that the finger points out in the direction of the current in the windings, and the extended thumb. So these fingers, these fingers, so they indicate what the direction of current, is it not? So that the direction of current here. The extended thumb, this thumb indicates the direction of the magnetic field, right? The solenoid is used to obtain magnetic field, uniform magnetic field. How? Let us see one by one. See, that is how, first of all, this solenoid is fabricated. We have to consider a soft core iron. Okay, so by inserting a soft iron core inside the solenoid, a large magnetic field is created, right? So mu B is equal to mu 0, mu Ni, mu 0, mu R into Ni. So this is the main equation. Do you understand? That is B is equal to mu into N into I. And this mu is already known as mu naught into mu R. So we can express in terms of relative permeability and permittivity through free space for certain medium, is it not right? Now, when a current carrying solenoid is freely suspended, it comes to rest like a suspended bar magnet. It acts like a bar magnet. So, the magnetic polarity of the current carrying solenoid is given by this end rule. We'll see one by one. Let us consider an infinitely long solenoid. It has n number of turns per unit length, carrying a current of I, that is in ampere. The length of the solenoid is very large, so we are assuming that it is very large compared to the radius. The magnetic field, remember, the magnetic field outside the solenoid is always zero, note this point. So the long solenoid appears like long cylindrical metal sheet. Therefore, the dots in the upper part, that is the dot in the upper part means here. These are the dots. These are the dots in the upper part and the cross in the lower part. Okay. You can also indicate here the dots in the upper part and the cross in the lower part. Okay. Now, so the dots in the upper part indicate the current sheet coming out of the paper, and then the dots lower cross marks, not dot, lower cross marks indicate the current sheet going into the plane of the paper. So when I put like this, it means it is coming out of the paper. When I put like this is coming inside the paper. After paper is a notebook, our notebook is a two-dimensional one. So we had to indicate the third dimension. How to represent that? So when I put this one means it is coming out from the paper. And what about this? Put a into mark means getting inside the paper. Likewise, we had to assume. Then to find the B at point B inside the solenoid, Ampere's circuital law can be applied. We just look at this. Let me consider ABC as the loop. So let me consider this A, B, C, D. Within this A, B, C, D, right? So there is a distance between D and C, H, right? And this is omega from from the center, from the axis of the solenoid, right? Now let us see, for ABC rectangular loop, we have considered the ABC rectangular loop, integral over the circle, that is cycle, is equal of B vector dot dl, that is equal to integral between the limits A and B of B vector dot dl plus B to C, because we had to consider as a rectangular loop. First, we had to consider from here, to here, A to B, B to C, C to D, and it should be completed, D to A. So we are considering this rectangular loop. I hope now you should be able to understand. So A to B, B to C, C to D, again D to A. So it has completed. Is it not a rectangular loop? So if L is the length of the loop, then we have integral over the cycle B vector dot dl vector is equal to BL. The path of integration includes the L turns. So the net current enclosed by the closed loop is given by this equation. I naught is equal to I into N into L. Now, according to Ampere's circuital law for the closed loop, it can be interpreted as integral over the cycle B vector dot dl is equal to mu naught I naught. Therefore, BL is equal to mu naught into I N into L. And from this, we can calculate the magnetic field that is equal to mu naught Ni. Okay. Right. So, thank you very much for watching this series of lecture.